Everyone in?
Yes.
Whoever is in. Yeah. Okay, let's start our next session today. Okay, so I left you with this slide. So what tells different kind of privacy notions and how differential privacy is different than secure function evaluation and homomorphic encryption. So now let's recap our definition of differential privacy. We have an algorithm A, which is a randomized algorithm. It is called differentially private if for all neighboring datasets. That means the datasets which differ only in one entry, D prime, and for all outputs S, the following relation holds, which is the probability that output of the algorithm A when trained with dataset D belongs to a set S is less than or equal to e to the power epsilon times probability of that the output of A when trained using D dash belongs to the same set S. And this guarantee is to hold for all datasets, all neighboring datasets D and D dash, and all outputs S. Neighboring means those datasets which differ only in one entry. This is what we saw earlier. Okay, now how can we design such an algorithm which achieves differential privacy? So this is our favorite dataset. We have n individuals, Alice to Zora, and we have their attributes. There are some non-sensitive attributes like name, postal code, age, and sex. And there is a sensitive attribute which tells whether the person has a disease or not. So this dataset is being passed to the randomized algorithm A, and the data users, which can be government, which can be researchers, companies, or can be an adversary. It can ask the randomized algorithm some query, and the algorithm will answer give the data users answer to the queries. This is the overall statistical database privacy framework. And differential privacy, the requirement of differential privacy is that for all neighboring datasets and for all outputs, the two distributions are close. Okay, so now think about this question: what fraction of the population has the disease? This is the query. And how can we release an answer which will satisfy differential privacy? That is our goal. So say we release this answer is equal to answer plus noise, which is of the order 1 by epsilon n. So this answer is the true answer. Suppose the fraction is say 0.7, the algorithm will release that 0.7 plus some small noise to the data users. The noise will scale, the level of the noise will scale as 1 by epsilon times n. Okay. So you see that we need very little noise to hide the individual's information. There are n individuals, and if we add noise 1 by epsilon n, if n goes to infinity, that means number of data points are very high, the amount of noise needed will be very low, and it will be sufficient for us to hide the individual of an information. That means if we do like this, obviously we need to specify what is the noise is, because the algorithm is randomized, right? So noise will depend on the randomization of the algorithm, right? So what kind of probability distribution we generate the noise from? We'll talk about that later. But you can think that if we add noise of this order, then we'll achieve epsilon differentially private. That means we can show this relation to hold for all neighboring datasets and for all outputs. Okay. But what is this scaling? Do we need this amount of scaling, that 1 by epsilon times n, or can we do add noise which is specific to the query? So if the query is different than this query, the noise could be different. So algorithm will ask noise add noise to the answer based on what query it was being asked. Not for that every query it will add same noise. It doesn't just make sense. Depending on the query, the algorithm will add sufficient amount of noise. Okay, and obviously we discussed that for meaningful privacy guarantee we need epsilon to be small enough. Think about epsilon is less than equal to 1. Okay, so now we'll talk about our first differential private mechanism. It is called the Laplace mechanism. So here, what noise we'll ask, we'll add the following noise. So in the answer, we'll add Laplace noise with error 1 by epsilon times n. Right? So this is the first algorithm, Laplace. With given a query, it will add Laplace noise with scale 1 by epsilon n. So still we are seeing that okay, the noise is not dependent on the query. So how can we make the noise dependent on the query? So before that, let's see some properties of the Laplace distribution. So Laplace is a continuous random variable. The probability density function of Laplace distributions looks like this, and B is the scale of the Laplace distribution. So the PDF looks like this. The probability density function with scale of a Laplace distributed random variable with mean 0. This is the probability that a random draw from this distribution takes value y is equal to 1 by 2b times e to the power minus of mod y divided by b. This is the probability density function of a Laplace distribution with mean 0 and scale b. So as you can see, if we change the scale, the PDF, this is a plot of the PDF. In the x-axis there is y, in the horizontal axis you put plot which is the different values, and the vertical axis are the probabilities. If scale changes, see the distribution changes, right? When the scale increases, right, see the distribution is getting flat. When the scale decreases, distribution is very narrow. So for higher scale, distribution has higher standard deviance, and lower scale it has lower standard deviance. So the scale actually determines how much noise you are going to add. If the scale is higher, you will add higher noise. If the scale is lower, you will add lower noise. So Laplace 1 by epsilon n, here the scale is b. The scale b is 1 by epsilon n. So this is the amount of noise we will add to the query. Obviously this noise is still independent of the query. So the mechanism is simple. Whatever the answer of the query is, just sample a random variable from the Laplace distribution with scale 1 by epsilon n, and whatever the sample you get, add it to the answer and send it to the data users. This is the differential private mechanism using Laplace distribution. Very simple mechanism. Alright, so this is how the density at y, if scale is 1 by epsilon n, this is how the probability density function looks like, right, for a particular value at y. We just replace b equal to 1 by epsilon n here, and you can see the density is proportional to e to the power minus epsilon n times mod of y. I'm just replacing b in this equation. This is how the density looks like. Okay, so now for every specific query, how much noise should we add? For every given query, right? The noise should be dependent on the query, right? So if query changes, we can add different kind of noise, different level of noise. Obviously the distribution will be same Laplace, but the scale of the noise will now depend on the specific query at hand. Alright, so any question till now about this? Okay, so if not, let's go to that. Okay, so we have a query Q, and the query dependent noise that we'll add now is Laplace quantity, which I'm referring as GS sub Q divided by epsilon. So here what I'm doing, I'm replacing 1 by n by this quantity global GS sub Q, which is called global sensitivity of a query Q. I'm replacing 1 by n by that. So for a given query Q, you will in the answer will add a Laplace noise with scale global sensitivity by epsilon. So what is this quantity now, right? What is a global sensitivity? So define this quantity. Global sensitivity of a query Q is defined using the following equation. You take any two neighboring datasets, the datasets which differ only in one entry. For every Q, you take for the data set D, take what is the output of the query, right? So if the query is number of for a given data set D, if the query is how much fraction has the disease, it is a number, right? So QD is just gives okay how much fraction is the disease has the disease in the data set. Now take another data set D dash, which differs from D in only one entry. Run the same query and get the answer. How much fraction of the people have the disease? So QD is the query value for dataset D, and QD dash is the query value for the dataset D dash. So take their difference, absolute difference, and do it for all pair of neighboring datasets. Do it for all possible neighboring datasets and report the maximum difference. So if you take a pair of neighboring dataset, find the difference in query values, and do it for all possible pairs and report the maximum. So this is the global sensitivity. So what does this signify? It signifies if you change a data set for a given query only in one entry, how much the output of the answer will change. Right? This only just signifies this global sensitivity. So noise should be will be proportional to this global sensitivity. So if the answer changes a lot, right? If the maximum possible answer changes a lot, we should add more noise. See, so you can see, right? If the answer changes loss very high, right? Then if we plot the distribution, two distribution will be very different. So to mask that high change, we have to add noise proportional to that. So if answer change is low, then if you remember these two graphs I have plotted, that the ratio that change will be very small. So the noise we need to add also will be very small. So this is how, so given a query, the noise that we will add will be proportional to the sensitivity of the query. Okay? Yes, so this is it, how sensitive a query is to change in one record in the dataset. Right? This is, so global sensitivity of Q characterizes the sensitivity of a query for only one change in the dataset. So this is our mechanism now. Given a query Q, fix your query, then whatever the answer, the algorithm, whatever the true answer is, algorithm adds a Laplace noise drawn from this Laplace distribution with scale global sensitivity by epsilon. Okay, this is our Laplace mechanism. So now there is a theorem that the mechanism A, which is the function of D, the dataset, as well as the function of the query Q, which what does the mechanism do? It takes the query value at the dataset D. So QD is the true value, true answer to the query, and add a Laplace noise with sensitivity, with noise proportional to global sensitivity of Q divided by epsilon. So this mechanism, if you release outputs based on this mechanism, it will satisfy epsilon dp in that definition. So this is the theorem. Alright, so I will prove this theorem in board. But before that, let's keep it for now. Let's see some other results and we'll come back to the proofs later. Right? I think, should we follow in this way? Or I can do it. Yeah. So we'll give a proof in the next lecture. And we'll also talk about the utility guarantee of Laplace mechanism. So all will be, we'll use a whiteboard for that. So we have now a mechanism, differentially private mechanism, which the theorem tells it is differentially private, and we'll prove it, and we'll also show some kind of utility guarantees. Okay, so now we'll go to some properties of differential privacy. So we told that, right? We have some requirements of differential privacy, that it needs to satisfy, needs to be robust to auxiliary knowledge. So why this is robust to auxiliary knowledge? Because this definition holds for all pair of dataset D dash and all outputs S. And no matter what the adversary knows, that doesn't feature here. So whatever the adversary knows, if your mechanism satisfies this equation, you can safely say that our mechanism is robust to adversarial knowledge. And what it does actually, so it bounds the relative advantage that an adversary gets by observing the output of an algorithm. When the adversary is observing the output of an algorithm for two data sets, so what is the relative advantage if he or the attacker would get So this definition will bound that. So that's why it is robust to this auxiliary knowledge. I see. So, okay, so what kind of knowledge we can, what kind of auxiliary knowledge we can protect us from? So attacker may know the data set except the one record that we are trying to protect, right? So it may note either D or D dash has been used for training. So except that one record, adversary may know the data set. Attacker can have any external source of knowledge, and even the algorithm, the DP algorithm can also be public, right? The DP algorithm that, okay, so this is the DP algorithm that we are using. We can also make it public, but only we need to hide the random coins of the algorithm. So algorithm do some randomization, right, by adding random noise. So the randomization we need to hide that. We can make all the other parts of the algorithm public. Only the randomization part we need to hide it. Okay. So we can publish, okay, we will do this, but only the randomization part we need to hide it, the noise part. Okay, this is the auxiliary knowledge, all the auxiliary knowledge an attacker can have. So this definition will protect us against all of this. Okay. Next property is post-processing. So yeah, someone in the break was telling me, so
Can you go back to the previous?
yeah.
So, I mean, a very basic question. I don't understand why the probability on the right hand side is smaller than the probability on the left hand side.
No, it's not like that. You have to have this relative ratio bounded.
So it's interchangeable.
It can be interchangeable. It's for the other part also true.
But D dash is like removing after giving one data point.
Yeah, removing, or you can think about, let's think about, you're just replacing one data point. Just replacing one data point. Okay. So and the other side also true. There is, you can put D dash here and D also here. Right? This is also true. So it's a symmetric argument. So all we care is we take the ratio and take the absolute value of that ratio, right? Or take the ratio and take, right, and or not absolute value, what? A logarithmic of that, and it has to be bounded by epsilon. Okay, now the second property is post-processing. So someone is mentioning to me during the break that what happens after we do DP, make an algorithm differentially private, and then we use that for a lot of other tasks, right? How much the privacy guarantee we lose, right? So we have ensured, okay, our algorithm is DP. So now we are taking algorithm's output and using it to some further downstream tasks. So whether information can get lost from that or not, right? So this theory, this property of DP will ensure that it will not. The theorem is here, okay, so you have an algorithm A which operates on a data set D and gives an output S, right? The algorithm A is an epsilon differentially private algorithm, and F what it takes the algorithm's output from this set S, right? A maps D to S and F takes S to some other set O, right? So F is operating over A. So this is any kind of pre-processing you are doing over the differentially private outputs. So F be any function, and it could be random function also. It might not be some deterministic function. It could be any random function. Then the compost algorithm, right, which is F compose A, right? The domain of the compost algorithm is still D because the domain of A is D, and the range of the compost algorithm is O, right? Because you are applying F over A, right? So range will become O. So the compost algorithm F over A, this also operates on the data set that we want to protect and gives a new output O in a different domain. We can show that this is also epsilon DP. So whatever post-processing step you do to the output of a differentially private algorithm, it will maintain differential privacy and the same amount. Okay. So what does it means, right? It is impossible to compute a function of the output of a private algorithm and make it less private. So privacy will not get lost, right? Will not get degraded. It is impossible. You cannot make a DP algorithm less private. We only doing this kind of post-processing. And then what it allows the data users to do whatever they want with the output of a private algorithm. as long as I, as an algorithm designer, I give a private algorithm, whatever the data users do with that algorithm, I don't care. I have achieved, I have, given privacy. We'll see the proof, but it will also be on board. Okay, so before going to the proofs, let me discuss another property. This property is called composition. So same question was asked again during the time of break. So we have told that okay, our algorithm is differential private with respect to a particular query, and we have done that for several queries. So now what happens if we compose all the queries, right? If we take the output of all the queries and try to build a final algorithm out of all the queries, right? So how much the privacy will degrade or whether it will remain same or not, right? So this property will tell that okay, if we compose the results of multiple query, privacy will degrade. So here you consider this picture. There are two algorithms A1 and A2. Both are taking the same data set D. So input to the both algorithms is D, and the output set of algorithm A1 is S1, and output set of algorithm A2 is S2. Okay. Not only that, algorithm A2 takes as one of the input its output. Whatever the output of algorithm A1 is also an input to the algorithm A2. So whatever algorithm A1 outputs, it gets feeded back to algorithm A2. Okay. We have this kind of algorithms, right? Think about, so what can be a good example of this? What kind of algorithm satisfy this, right? So you run an algorithm, gets an output. Second round, you run another algorithm which gets the previous output as well as the data set. Think about any streaming algorithms, kind of any online kind of algorithms, which will take input as previous rounds output. So any online learning algorithms, any streaming kind of algorithms will have this kind of flavor. The final algorithm is the composed algorithm A. So let us define that formally. So A1 is a epsilon differentially private algorithm. A2, its domain is S1 times D and its range is some set S2. Say A2 is epsilon 2 dp, right? So A2 takes two inputs, data set D and output of A1, right? So domain is S1 cross D and its range is S2. Say we have these two algorithms, both satisfies dp, A1 satisfies epsilon 1 dp, A2 satisfies epsilon 2 dp. And so what does this mean, right? A2 takes domain of A2 is S1 times D and range is S2 and it is epsilon 2 dp. That means for all outputs small s1 in the set of this capital S1, right? So small s1 is like all kind of outputs of algorithm A1, right? For all S1, the function A2 of S1 dot is epsilon 2 dp, right? So take any output of algorithm A1, pass it back to A2. Still A2 will be epsilon 2 dp for all such kind of outputs. This is what we are assuming now. So A1 is epsilon dp, A2 is also epsilon dp. Then what will happen if we compose these two algorithms A1 and A2, right? Let A be the composed algorithm whose domain is D and whose range is S1 times S2, right? So A is the composed algorithm, this dotted line is the total algorithm whose domain is D and which range is S1 cross S2, the Cartesian product of the two sets, right? It's a composed algorithm. So what is the output of A? A outputs two numbers, S1 and S2, right? Where S1 is what? S1 is the output of A1 ran on dataset D, and small s2 is output of A2 ran on the dataset D and taking the output of algorithm A1, which is S1. So S1 is A1D, and S2 is A2 of S1 comma D. So, and output of the composed algorithm A is S1 comma S2. Okay, this is the output of the algorithm. So then we can show that the algorithm A is epsilon 1 plus epsilon 2 dp. So what is happening here? If two algorithms are differentially private with some parameters epsilon, So these parameters are simply add up if we just do some basic composition of these algorithms.
So I have a question. So when you define this K2's epsilon to differentially privacy, so you are saying that S1 is kept fixed and D is allowed to vary, right? In the definition. So is this definition same as the one that you were showing?
Yeah, you have the variable in D, right? S1 is a fixed.
So this is a stronger requirement.
No, this is it's a privacy with respect to D. We are not trying to make privacy with respect to others. Privacy with respect to D. Okay, so composition tells if you take two differential private algorithms and compose them together, the privacy guarantees will still simply add up. Okay. So yeah. So what does it allow? If we do multiple queries on the same data set, so A1 answers one query, A2 answers another query. So you can give a bound on the cumulative privacy on the entire on different queries where the queries are asked on the same data set. So take same data set, ask two different queries, get two outputs, and publish both the outputs together, right? Release both the outputs together. So if each output of each query is differentially private, then output of two such queries will be 2 times the privacy guarantee. All right. So it's not that we only can do it 2 algorithms. We can extend easily to k such DP algorithms, or k is some number, k is some your favorite number, or that means k such queries. So what we can say, if there are k number of queries and each of algorithm satisfies epsilon DP, then what will be the total guarantee of the total privacy guarantee of the algorithm? Anyone? So each algorithm A is epsilon DP. So we have k such algorithms. We compose them, right, and give a final algorithm. So what is the total DP guarantee? K times epsilon. Right? So we can see that cumulative privacy will scale with the linearly with the number of queries. So now you can see that, okay, if the number of queries are very high, so we're losing, right? So k times epsilon means if epsilon is say 1, so k times epsilon is k, right? So this ratio, the bound on the ratio of these two outputs are getting very high, right? So we're losing out on privacy because the composition is linear. It's a linear composition. So can we do better? Yes, this bound can be improved using something called advanced composition, which is obviously an advanced topic, as the name suggests. We can show that cumulative privacy scales sublinearly with the number of queries. So basic composition, if you just do these basic things, you can get linear in number of queries, cumulative privacy scaling. But if you do some advanced sophisticated stuff, you can get cumulative privacy scaling with sublinearly with number of queries.
So what is the need to add more algorithms if we decreases the...
So suppose you are training some very complicated algorithm, right? Say a stochastic gradient descent. Have you heard about stochastic gradient descent? So what it does, right? Every round it samples a batch and run a gradient descent on that. So that is one algorithm, right? Because you have sampled a batch, right? Or say take the whole data set and run a gradient descent on that, right? So you get an output, right? What you do in the next step? You do run it again, right? And how do you do that? You use the previous what is stochastic gradient descent outputted in the first round. You will iterate on that, right? So this is the output of stochastic gradient descent in the first round. It has been used by algorithm A2 to iterate on the second round, and the same data set is being used. So it keep on going, right? Number of rounds, right? So number of rounds here is your number of queries. So it's not what is the need, it is in the practical case, right? You need to build a complicated or build a fancy ML algorithms. You need multiple copies of algorithms run together. So for that the need arises. So now if you run a private version of stochastic gradient descent, right? How much privacy you will keep on losing as number of queries or number of rounds increases, right? So composition is a very important result in that sense. Yeah.
Sir, you're going to adjoin k different of these basic things. So if the ith algorithm using only the output
Yes, ith algorithm can use I output from all previous 1 to I minus 1.
That setting it has.
Yeah. It can output from all the previous 1 to I minus 1. Okay, the question was whether it just do it this kind of things, right? A2 takes output of A1 as an input. So what happens if I add A3, right? Will it take output of A2 or it can take output of A1 also, right? So this kind of composition. So the answer is A3 can take output of A1 and A2 both as inputs. And the advanced composition will tell that if you do this case such things, or any composition will tell if you do case such things, privacy will degrade over the number of compositions.
Hey, sorry, one more question. Can I go back?
Yeah.
So here when you say that this guarantee holds for all S1 belongs to capital S1, right?
Hmm.
So S1 itself is a function of D, right?
S1 is a function of D. Yeah.
So when you say that D and D dash, so S1 also changes.
S1 also changed. Sure. No. So this is that's why, right? It's for all S1. So we'll fix some S1.
Okay.
So when we prove it,
So then D can only vary in a particular way, right?
no. D can vary in D can vary only. No. D can vary
S1
anyway.
is still fixed.
We show that for all S1. Take any S1.
Sure, but what I'm saying that when you write that A2 bracket S1 comma dot, that S1 is itself S1 bracket D.
S1 comes from D, yeah. But when we'll prove it for all S1.
Sure, you can prove it for all S1. What I'm saying is that when you change D to D dash, that S1 bracket D also
Yeah, it
changes
will
to
change,
S1
yeah.
bracket D dash. Right?
Yeah, it will change.
So for that, so this is not that the S1 is kept fixed by force and then.
No. When we'll make it forcefully fixed. Make it forcefully. When we prove it, we'll make it forcefully fixed to
But
some
then
S1.
in that case, D and D dash will be related in a certain way.
Yeah, maybe. Yeah. Okay, yeah. So proof also will be in board. All right. So yeah. So now let us give some what is the benefit of this composition. So that's what I mentioned, that if you are running multiple algorithms together, then composition is an useful tool. So if what composition tells us, if A is an epsilon dp algorithm for one query, then it is k epsilon dp for k queries. That's what composition result tells us. So now suppose you are running an algorithm, okay, which has to answer these multiple queries. Like think about this stochastic gradient descent, it will run for k different number of rounds, right? So, but here is the budget. You want your final algorithm to satisfy a particular amount of privacy. That budget, right? You cannot keep it running for a long so that privacy guarantee degrades. So someone has given you a budget. You are an algorithm developer. Someone has given you a budget. Okay, you are allowed only this amount of privacy loss, which is epsilon naught. This has been given to you. And also you have to now run the algorithm for k such queries. So how do we do it? So one thing is easy. You need to set every epsilon is equal to epsilon by k, right? So for every query, you run A such that A is epsilon by k dp, right? If you can ensure A is epsilon by k dp, then the composition of k such A's will be epsilon dp, right? So that means you are making, given an epsilon, if number of queries are higher, you set to make epsilon to be epsilon naught by k, right? Epsilon will decrease, right? So previously, if your algorithm A was epsilon private, say epsilon is 0.5, it gave you some amount of privacy, right? So now you need to make sure now your epsilon should be more private than before, right? So because you have given a budget epsilon naught, say epsilon naught is also 0.5 and say k is 10. So current now you have to set epsilon equal to 0.5 by 10, so it will be 0.05, right? So you need to make sure each algorithm now more private than previous, so that overall 0.5 privacy is preserved, right? That's how you will account for the privacy. So given a particular privacy budget and given the number of queries, you need to make good accounting of the privacy. How much that whenever you have answered one query, you need to keep an account. How much privacy I have lost, right? So that my total overall privacy after k queries doesn't exceed the budget. So this time, whenever we run this kind of online stochastic gradient descent kind of algorithm, we need to keep on accounting for the privacy as well. So more queries, if we have more queries, obviously we need smaller epsilon for each algorithm. And what will mean that? Smaller epsilon will mean higher privacy, as well as we know there is a privacy utility trade-off, right? If privacy increases, utility will go down, right? So smaller epsilon will make privacy high, so utility go down. So we'll have less accuracy for answering each query. So this is the trade-off is visible here. Okay, so now also we need a trade-off between accuracy and the number of queries, right? So we cannot run our stochastic gradient descent algorithm for as many rounds as possible, right? Otherwise, the privacy needed for each run of the query will get on adding up, right? We need to find a good trade-off between how long we should run our algorithm, right? For how many rounds we should run our algorithms. So that is also needed when we run an algorithm. Okay, so what does this composition and privacy accounting tells us? It allows us to design differential private algorithms which can ask multiple low sensitivity queries, as well as which should tolerate noisy answer to all the queries. Right? So this is what we are giving. Classic ML example is stochastic gradient descent. So we have multiple low sensitivity queries for every round, and a noisy answer to each such query. And when we do that, over the time we'll keep on adding that. Okay, that's, I think it's the last result before we should go to the board. So this is another property of privacy, which is called group privacy, and it will help us to set epsilon, right? So epsilon is what? Epsilon is what in our hand, right? So how much privacy we need to ensure our algorithm to have, right? We can set epsilon. If we set epsilon to be very small, privacy will be high. If very low, privacy will be low, right? So given a data set, what epsilon should we set, right? So group privacy will give us some idea on that. Okay, so here's the result. So you have set two data sets, D1 and D2 of n records. Instead that differ in k positions. So till now we are considering only data set that differ in one position, right? Now think about two data sets that differ in k positions. Now k can be 1 to n, any number, right? Think about what does this mean? Think about if a data set, what does that mean, right? Think about, so each individual's data is appearing in multiple entries of a data set. In those kind of scenarios, if you replace that individual completely to construct your another data set, so k entries will get replaced, right? So my data is in one data set 10 times, right? So when I am constructing another data set, and I thought that, okay, let's remove my data completely. So if I remove my data, so all the k entries, all the 10 entries will get removed, right? So the notion of neighboring data sets now goes from one record changing to k records changing, right? So now think, if an algorithm is epsilon dp, algorithm A is epsilon dp, then for all outputs we have probability that first we run the algorithm on the dataset D1, we get an output. Probability that output of A when run on D1 belongs to the set S is less than or equal to e to the power k epsilon when we run it on the another dataset D2. So D1 and D2 is now differing in k entries, not one entries, because one individual's data you have replaced, and if the individual's data was repeated in the dataset, so all the repeated entries will get replaced. So now what will happen if the dataset differ in k positions? E to the power k epsilon comes. If k equal to 1, this is our standard notion of differential privacy. It will be e to the power epsilon. If k is a generic number, it will be k epsilon. Right? So yeah, as I mentioned, so this is different than composition. We're not composing any mechanisms, right? It is like data set is like that, so this kind of privacy loss will suffer. So, when this is useful, so as I mentioned, this is useful when we want to hide participation of a particular individual who contributes several records, right? So I am an individual, my data is in several records, right? So then it is useful because I contribute k records. So if my data is being replaced, so k records will be replaced. And obviously it is also useful when, say, every individual has only one data, but there is a group of individuals whose data are strongly correlated. Think about a family. A census, when it is built, a family information is collected. So every member of each family data is there. But it's highly likely that data of a family is correlated, right? So if you can infer the data of the head of the family, maybe you can infer the data of the child of the family. So when groups of people whose data are strongly correlated, then we should ensure the entire group's data is protected by using differential privacy. We should not focus on a particular individual. We should focus on the entire group. And obviously to do that, we'll suffer some loss in privacy. Okay, so now this group privacy tells that we need to set epsilon larger than 1 by n for reasonable utility. So can you guys tell me why? Why we need to set epsilon greater than 1 by n for reasonable utility? Yes?
K is less than n, so we want the overall thing to be less than 1.
Okay. So this is one possible answer. But any other? Okay. So group privacy will tell us, okay, we need to set epsilon is greater than, at least greater than or equal to 1 by n. So why? The reason is, think about epsilon is much less than 1 by n, right? Epsilon is very small, much less than 1 by n, right? So epsilon is that small, right? Right? Then whatever the number of differing positions k, right? Whatever the number of different positions k is, say k is n, so n positions are different. Still, what will happen to k times epsilon? Epsilon is much less than n, 1 by n. K is n. What will happen to k times epsilon? It will be very small. It will be close to 0, right? So e to the power k times epsilon will go to 1. So then what will happen? This inequality will become equality. So our two data sets d1 and d2 that differ in k, which is n, that differ in n positions. All the positions are different. All the records are different. Still, the probability distribution of their outputs are same, right? So because this inequality will go to equality, the probability distribution of their outputs are same, even if d1 and d2 are completely different data sets, right? So if we set epsilon less than 1 by n, we will get this answer, which completely violates. Okay. So what the algorithms do, if we set epsilon much less than 1 by n, to ensure high privacy, what the algorithm will do, it will just ignore its input. It will just report junk. Right? So we do not want those kind of algorithms because we cannot do anything with that. We will achieve privacy, right? K epsilon, to make it small, right, will achieve privacy, but algorithm will ignore the input and it will just report some junk value. So to make our algorithm useful, at least, we need to set epsilon greater than equal to 1 by n. So any number of data points, we need to set like that. So this group privacy will give you some idea how to set epsilon given a data set. Okay, so I think next is, okay. Yeah, so this is a corollary that DP algorithms won't be able to give useful output for small data sets. So if n is very small, then DP algorithm won't be able to give a very useful outputs. So proof is in board. So when is the break time?
We can
Break now, right? Yeah. Or yeah, let's break now. Yeah. And next lecture will be on board.
Can we meet in 2 minutes? Or
Yeah.
we'll have a break for 10 minutes.
Okay. So yeah, I promise that I will give proofs for Laplace mechanism's privacy as well as some results on utility. Then I have to give you proofs for the properties of DP. There are three properties we have discussed. One is post-processing, another one is composition, another one is group privacy, OIC. Okay, so we'll start with the proof for privacy of Laplace mechanism. So let's now recall a bit what was Laplace mechanism. So algorithm A, okay, algorithm A, yeah, takes a data set D, bigger, not visible. Is it visible, guys? People in the back, if you are watching, just tell whether it is visible or not. So the input data set is D and here query is Q, right? This is the mechanism. What it does, takes the data set and query as input and it outputs the query value, the true query value Q of D and a Laplace noise with it, with global sensitivity, with the scale GSQ by epsilon, right? This is a global sensitivity, right? So what was global sensitivity that we have defined? Global sensitivity of a given query Q is the maximum difference between the query value for two datasets D and D dash which are neighboring, right? So D and D dash, by this notation we are telling that D and D dash are neighboring. That means it differ only in one inch. So this is the definition of global sensitivity and this is your mechanism. Now we have to prove that this mechanism is private, right? Okay, so for that first, let we introduce some notation. Let Q of D is mu and Q of D dash is mu dash. Then what is global sensitivity? If we introduce this notation, Q of D is mu and Q of D dash is mu dash. So just put it back here. So I will get maximum over all neighboring datasets D and D dash mod of mu minus mu dash, okay, which I define this as delta. I define this maximum value is delta, or for the sake of generality I can say that this maximum value is upper bounded by delta. So delta is basically an upper bound over the global sensitivity of a query key. Alright. Okay, so now let us recall again the probability distribution function of Laplace distribution. PDF of Laplace, okay, with mean mu and sensitivity, not sensitivity, what is it? Mean mu and scale B. So instead of mean mu, because I have this notation, let's mean M and scale B. So how does this look? So PDF, so probability of a particular value y is 1 by 2b e to the power minus y minus m divided by b. Okay, this is the probability density function of Laplace distribution, where y is any number in the real line. Okay, this is the probability density function of Laplace. So all we'll use all these definitions to prove that our Laplace distribution is private. Okay. I see. So what is our Laplace? What is our Laplace mechanism? Okay. So our Laplace mechanism we are writing using this. This is our Laplace mechanism. Let it write in terms of this upper bound delta. So what I am writing, a modified version of Laplace mechanism which uses the upper bound delta over the global sensitivity. So A dq is the true answer qd plus Laplace with scale delta by epsilon. So where delta is the upper bound on the global sensitivity. These are some modified version of the Laplace mechanism. Similarly, what will happen if our data set is d dash? So A d dash of q is q of d dash plus Laplace delta by epsilon. Okay. So now we are trying to prove the differential, prove that Laplace is differentially private. So for that, what do we need to show? We need to bound the ratio of probabilities. When the one thing the input is d, another case when the input to the algorithm is d dash. So we have to bound the ratio of these two probabilities. So take this probability of for the mechanism, the algorithm A, when input is d, query is q, right? What is the probability of A dq is equal to some output y, and we divide it by the probability of the algorithm A with data set is now replaced to d dash q equal to y. If we can bound this ratio by e to the power epsilon, then we know that our algorithm is differentially private, and we have to do it for all y. So for all y in R, real line, we have to do it. So what for this, let's just fix n y. If we can do it for n y, then we can do it for all y. Okay. So let us now write the probabilities in terms of this PDF of Laplace distribution. So you can see ADQ is a random variable, right? By this you can see that ADQ is a random variable. It is given by QD plus Laplace of delta by epsilon. So can you tell me what is the mean of this random variable ADQ? It's QD, because Laplace with zero mean is given by this, right? With mean m given by this, right? And if put m equal to 0, and this is Laplace of delta by epsilon. This is like Laplace with zero mean, right? So basically I should write more carefully. This is, I should write that Laplace of mean 0 and scale delta by epsilon. And here also mean 0 and scale delta by epsilon. So basically what we are taking a distribution and shifting it by a number qd. So the mean of this random variable ADQ is qd. Similarly, mean of this random variable AD dash q is qd dash. So what is ADQ? ADQ is a Laplace distributed random variable with mean qd and scale delta by epsilon. AD dash q is similar, Laplace distributed with mean qd dash and scale delta by epsilon. So let me write that. So here this implies ADQ is drawn from Laplace with mean qd and scale delta by epsilon. Similarly, A d dash q is drawn from a Laplace distribution with mean q d dash and scale delta by epsilon. Okay. So we know the probability distribution of these two random variables. We need to bound the ratio of their probabilities. So what we will do, we will use this formula. We know probability of y is given by this. So what is the probability of ADQ equal to small y? Right? So it is given by exactly this formula. The numerator is 1 by 2b. So in m, I will replace m by this mean QD and replace scale b by scale delta by epsilon. That's what I am doing. I replace 2b by 2 delta by epsilon.
One question.
Huh?
One question that like writing this QD plus Laplace 0 and that is same as this distribution. That is not obvious to me. I was trying to think.
See that, okay, so think about
I
some z. Z is drawn from this and then shifting. You are having a mean zero distributed random variable and shifting by now.
Laplace is a location family, so just add something in the location parameter.
So on.
Yeah, okay. Fine.
Even if you are
Yeah, fine.
worried about that, I am writing it is probably y and you have to use a distribution function. That makes sense. This is not completely correct,
Yeah.
but you can think that
No,
okay.
no, I
you are
got
right.
it. Yeah, yeah, fine.
So let's ignore that. So we are writing, so doing replacing b by delta by epsilon. So we have 2 delta by epsilon e to the power minus y minus, I have to replace mean by this qd, and here is also b is delta by epsilon, right? Am I making any mistake? No. So b is delta by epsilon. This is our numerator, and similarly this is our denominator. Same thing, 2 delta by epsilon e to the power minus y. Now the mean is qd dash. Data set has changed by delta by epsilon, right? So let me be more careful. All right. So what will happen? These two will get cancelled. Okay. And I'll put this numerator to the denominator to the numerator. So it will be e to the power minus epsilon by delta to y minus qd and y minus qd dash, right? I think it's correct.
So we'll use triangle inequality after this.
Exactly.
No, not triangle. We'll just use two delta.
Huh? No, we'll have to use triangle. Okay. So this is what we have, right? So we have defined qd is mu and qd dash is mu dash. Let's do that. E to the power let's write E as x, right? It's better. Okay, so I'm just replacing qd by mu and qd dash by mu dash. We have defined it like that. So now see how to write this, right? Is everything correct? Yeah. So we have to bound this y minus mu and y minus mu dash, right? So note that triangle inequality gives you triangle inequality will give you the following. It basically tells you that no, I think some mistake is there, right? No, it's okay. Yeah.
So y minus mu we can write as
Yeah, so triangle inequality gives this, right? Yeah. Y minus mu minus mu dashed, right? Minus y minus mu. Is greater than or equal to mu dash minus mu.
lesser than.
Minus, right?
Okay, fine.
Minus is greater than or equal to mu dash minus mu.
So lesser. So the first term y minus mu dash and it will be y minus mu dash you can write as in the
Yeah.
bracket y minus mu plus mu you have plus minus mu inside. Right? And
So
then
let's stick to this. Let's stick to this. Yeah. So I think less, right? Yeah. Sorry, this is less than, right? Is correct? Yeah. Yeah. Okay, this is triangle inequality, which is give you that. I think we should just put it back, right? Yes. So now what we'll do? We'll do this, the opposite thing.
let's put it back to get it to the power of 7.
Yeah. So and now we will bound this thing mu dash minus mu by delta from here, right? Mu minus mu dash is bounded by delta, so it is bounded by delta. So what we'll have this, right? We'll interchange the sides. We'll have y minus mu minus y minus mu dashed greater than or equal to minus delta. So we have this. Correct, right? We have greater than or equal to minus delta. So we have bounded this quantity. Yeah, we have bounded this quantity as greater than or equal to minus delta. So we have to put it back. So we have e to the power minus delta times this, and this is greater than or equal to minus delta. So let us put this thing back here. So we can upper bound this thing by less than or equal to e to the power minus epsilon by delta times minus delta. Right? So this is a minus in front, that's why this is greater than or equal to. If we do it minus, it will become less than or equal to. So this minus, this delta gets cancelled, minus gets cancelled, we get e to the power epsilon. So this is a proof of your privacy of Laplace mechanism. So this is upper bounded by e to the power epsilon. Okay. So I have gone there. All right. This is a proof of privacy of Laplace. So let's do some utility analysis. Okay. So what are we doing here? Laplace, right? So this is our Laplace mechanism. A dq is our output of the mechanism. It takes the true value of the query qt and adds some Laplace noise, right? So this is the true value. This is the true value of the query. And ADQ is the reported value, which is obviously noisy. It's a reported value. So the measure of utility of this mechanism can be defined by the differences in these two values. What is the reported value and what is the true value, right? So we define error of the Laplace mechanism. Okay. So error of Laplace mechanism, or you do define squared error of Laplace mechanism. Error of Laplace squared error of Laplace mechanism we define as the difference between these two and squared it up.
Sir, we have to show this probability ratio bound for any subset S, but
Yes.
here we have given the density ratio bound for a singleton.
Singleton one, yeah, true.
So that part needs to be completed.
Yeah, that part needs to be completed, yes. So this holds for all y, right? So now you have any subset S, right? You write as a union of singletons. You have this holds for all y.
Yeah.
Now take a set S, you can write it as singleton of all y's, in union of all the singletons.
That could be uncountable.
So but it will hold. It will just hold. Okay, this is for all y, so you can complete this argument by taking a set S. How? Because it's a density function. That's why it gets completed. So instead of y, you can put a measure of the set. Think about, you can just write a singletons, and it is hold for all y. This is just a ratio, right? So it will hold for the.
It's not that obvious actually.
Okay, we'll discuss this out of this. But the thing is, it holds for all y, that's why it will hold for a measurable set. So error of the Laplace mechanism is ADQ minus Q of D, right? QD is a true value, and we are taking a square, so it's a squared error. So we have to bound this. If we can bound this, we can bound the error of the Laplace mechanism, and if the error is smaller, then we know that okay, we have good utility. So note that ADQ is a random variable, right? It is a Laplace distributed random variable. So we need to take an expectation. So average squared error is expectation of this quantity ADQ minus QD whole square. Okay? This is average squared error. So you need to compute this. And the expectation is over the randomness of the algorithm A. So you need to compute this. How do we do this? Expectation of the squared of a random variable, which is Laplace distributed. We will use the PDF to compute this. Okay? So this is given by integration of, how do we write it? Y square times probability of that the random variable ADQ minus QD is equal to y. Integration of dy, right? Correct? So and now we have to integrate over all possible y, which can take values from minus infinity to infinity. So basically, taking this, I think, using this PDF. Okay. So what? Now see this random variable. What is this random variable? ADQ minus QD. What is its mean and what is its scale? Mean is QD. No, where I'm going ADQ minus QD, right? I subtracted the mean already. So ADQ is Laplace distributed with mean QD. We're subtracting the mean 0. So it's Laplace distributed with mean 0 and scale delta by epsilon, right? So I will put m equal to 0 here and b equal to delta by epsilon here. Y square m is 0, right? Okay. Right. dy
You wouldn't have the 2 there, right?
at the
In the exponent.
What?
2 is not here.
oh 2 is not here, right? Yeah, 2 delta by epsilon, right? So if we now we need to compute this integral to compute this, right? So I will not compute the integral for you. I'll just give the answer. The answer will come as 2 into delta square by epsilon square. Okay, so can you guess why the answer coming like that? If we do the integral, it will come like that. Can you guess why it is coming like that? Why it will be 2 into delta square by epsilon square? So the fact is, if fact here that I am using, yeah, I write fact here. Fact, the variance of a of the distribution Laplace 0 comma b, a Laplace distribution with mean 0, which this distribution has mean 0, and scale b, this distribution has scale delta by epsilon, is 2 into b square. Okay, the variance of the Laplace distribution is 2 into b square. If you compute the variance, you will get it. So I am just using that. The expected value of y square. This is like expected value of y square, and since the mean is 0, so this is equal to variance. Any question here? Did you able to understand why this is equal to variance? So what you are doing, right? What this equation gives, right? This equation gives integration minus infinity to plus infinity y square into p of y, right? P of y. But p is the probability density function of Laplace. Py with in dy, right? So what is this? This is expected value of y square. This is if you compute expectation of y square under this Laplace distribution, it is like this. And since this is a zero mean random variable, so this is zero mean. Does that mean that expected value of y is 0? So if you you combine this together, variance of y is given by expected value of y square minus expected value of y or whole square. This is variance of y, right? You know about variance? So now this is 0. So variance of y is equal to expected value of y square. So this is expected value of y square, which is exactly this. Expected value of y square, where y is distributed accordingly to Laplace with mean 0 and scale delta by epsilon. And the fact is variance of Laplace with mean 0 and scale b is 2b squared. So b is delta by epsilon, and we put it, we get it. Okay, so this is the result of this. I'm erasing this part. Okay, so now let's prove some properties of dp. First property will prove post-processing of dp. So what was the definition? That A is an algorithm from D to S is epsilon dp, right? And f is a function from S to O. So I am giving the proof when f is a deterministic function. However, the proof will hold for f is a random function. That will be your exercise. I will not prove it for random function. I will just prove it for deterministic function. So A is d to S is epsilon dp. F is a deterministic function. Then A compose D, F compose A. Whose domain is D and range is O is also epsilon dp. This is the statement. Okay, so the proof is very simple. So think about this event that, so what do we have to prove? First write that, right? So for all small o in capital O, we have to do this, right? We have to show that, we have to compute this, the probability, right? Probability of f of A of D, right? Probability of f compose A of D equal to small o. Right? That you have to do for all small o and big O. For all outputs, right? You have to compute this, right? So now, if f is deterministic, this probability is equal to probability of AD is f inverse of O. Right? Any question here?
AD belongs to
AD belongs to F inverse, right? You are right. AD not F inverse. AD belongs to F inverse. Okay? Everyone understands why this is the case?
Pre-image.
Huh?
It's the pre-image.
Exactly. So exactly F inverse O is a pre-image, right? F inverse O is the pre-image of O under F. Pre-image of O under F. Right? And so the event, this is the event, right? There are two events. F compose AD is equal to 0. This is one event, and this is another event, right? AD belongs to F inverse of O. These two events are same under this probability, because F is a deterministic function, and so F inverse O is a pre-image of O. So this is true. Now we know that A is differentially private, right? And what is that? F inverse of O, right? So F inverse O belongs to S, right? So think about this. This is a data set D. A takes a data set to S, and F takes it to O. And F inverse maps it back to S. Okay. So F inverse O lies in the set S, right? So we can use the DP guarantee of A. So what was the DP guarantee of A? Let me write it here for your reference. So DP guarantee of A was probability that AD belongs to S if less than or equal to e to the power epsilon into probability of AD dashed belongs to S. Since A is epsilon dp, this holds, right? So we'll just use that. So AD belongs to S, this is less than or equal to this. We just use that here. We'll use that here, and what we'll get? This is less than or equal to e to the power epsilon probability of AD dash belongs to F inverse of O. So I'm just replacing S by F inverse O here. Okay. So now think about this. AD dash belongs to F inverse O. This is similar as the event AD. F of AD is equal to O. F AD dash is equal to O. This is the same as this event. Similar argument from here to here. Right? So I will write probability of this event is equal to probability of this event, and there is e to the power epsilon in front, so it will be e to the power epsilon. So we started from here, probability of F AD of equal to O. Now we have is less than or equal to e to the power epsilon, probability of F AD dash is equal to O. So this proves that F of A is differentially private. This holds for all O. Now we can obviously do this singletons, take any set in capital O and think about any set is union of singletons, and you can extend the proof to for any set. So F of A is epsilon differentially private. Okay. So we have post processing. Now we'll prove composition. Any question? I will remove this, I think. Let's do composition now. So what was our result? Composition. Remember that was this kind of diagram, right? This is A1, this is A2. A1 takes D, gives S1. This gets feedback to A2. A2 takes D, gives S2. Right? And there is so same D, right? Same D. Same D goes here. And you make a composite algorithm. Sorry. Take the composite algorithm, right? We call this composite algorithm A. That was our diagram. It was very badly drawn, but I think slide has a good drawing. Okay, so what we had, right? We had this A1, which takes D and outputs S1 is epsilon 1 dp. We have A2, which takes S1 cross D times S2 is epsilon 2 dp, right? That we had, right? So now our theorem was A, which takes D and gives an output in S1 cross S2 is epsilon 1 plus epsilon 2 dp. That was our theorem. Okay. All right. Okay, so how does the output of A looks like, right? Any output of A looks like output of A are given by these numbers small s1 comma small s2, where small s1 is basically A1 of D and small s2 is A2 of small s1 comma D. Small s1 is dependent on D. Okay, this is how the output of A looks like. So now we have to show that A is dp, right? So let's try to do that. Let's do here. Okay, let's do here. We have to show that probability of AD is small s1 comma small s2. Fix some small s1 comma small s2. Fix one output of A. This is, how do we write this, right? So we write this as following. This can be written as probability of, now we'll divide A into two parts, A1 and A2. This can be written as probability of A1 of D equal to S1 into probability of A2 of S1 comma D is equal to S2. Can you tell me how can we write this? Can we just decompose A to A1 and A2? Have you heard about independence of random variables? So A1 and A2 both are randomized algorithms, but they have their own random coins, which is independent of each other. So independence of random variables give you this. So joint distribution, it is a joint distribution over randomness over both the algorithms randomly. Joint distribution where the randomness is coming from both the algorithms. So a joint distribution is product of marginal distribution. So here the randomness is only in A1, here the randomness only in A2. It's a marginal distribution. So independence tells you joint distribution is the product of marginal distributions. Independence of random variables. So this is coming from independence of random variables. Okay. Now we know what A1 is dp. So what that means, A1 is dp means this is less than or equal to e to the power epsilon probability of A1 of D is equal to S1, right? This is because A1 is dp. Okay. So you also know that A2 is also dp. But so A2 takes something from S1, right? A2 has domain S1 also. So what does this mean? This means A2 S1 comma this, right? For each S1 in capital S1, A2 is dp. For all small s1 in capital S1. This is what we are basically hypothesizing. For all small s1 in the output space of capital A1 algorithm, for all small s1s, A2 is epsilon 2 dp. So we can use that. So we have fixed some s1. We can use this. This is from here that this is epsilon dp. So this will be e to the power epsilon 2 probability of A2 into S1 cross times D. What? D dash. Sorry. D dash is equal to S2. We are crucially using that A2 is epsilon dp for all S1. Okay. So what we will do? We are now this. We'll just combine these two. We have e to the power epsilon plus epsilon 2 and this term probability of A1 d dashed in S1 okay. Now we'll use independence again to combine these two. I'll come. Okay, so we started from here and we proved that probability of AD equal to S1 comma S2 is less than or equal to e to the epsilon plus epsilon 2 into this. So hence we prove the theorem. Yeah.
Sir, what are exactly the random variables here?
Random variables is not, it can be any random points in A. You can think about Laplace. Laplace can be random variables. So A1D is a Laplace mechanism that I told just right now. A2D is also a Laplace mechanism.
Can we consider it as a like the product as a conditional probability?
Exactly. This is product. So this is actually why this is true, right? This is probability of x comma y. X and y two random variables. This is given by probability of x into probability of y condition on x. And now since x and y are independent, probability of y condition of x is equal to probability of y. We are using that. The independence of random variable uses that. 5 minutes. Last proof. Okay. Let's remove post processing. Okay, so now we are doing post processing. We are doing group privacy. This is the third property of DP. So A is epsilon DP. So that these are the statement. Consider two data sets D1 and D2 that differ in k entries. That differ in k entries where k is less than equal to, greater than equal to 1, less than equal to n. Right? Then the theorem was probability of AD1 belongs to S, and S is the output, is the range space of A. Is less than equal to e to the power k epsilon probability of AD2 belongs to S. Okay. This we have, right? So now how do we prove it? Take this data set D1. It has 5 entries. D1, it has 5 entries. And take this is another data set D2. It also has 5 entries. Now assume 3 entries are different in D1 and D2. Say this one, and this one, and this one. These 3 entries are different because k is equal to 3 here. Okay, in these data sets. So now we are allowed to do the only one thing, because in DP we know that we can prove DP guarantee for data sets which differ in only one entries, right? So now how can I make myself shift from here to here? So how to design some intermediate data sets so that I can gradually shift from D1 to D2. Okay. So what I will do? I will first define another data set. I call it. So first I rename D1 as D naught 0. Okay. And D2 as DK. So both these two data sets differ in k entries. K entries, right? But I can prove differential privacy for two data sets that differ in only one entries. So what I'll do, I'll define an auxiliary data, a different data set D1, right, which differs from D0 in only one entry. So what I'll do, I'll keep this all the same. Okay. So I know this 3 needs to be changed. So I put this here and keep this 2 here. That means I only differs only one entry. This D0 and D1 differs only in one entry. Right? Similarly, I do D2. D2, what it will do? It will take D1 and change one more entry. So it will have this. Similarly, we have this. I'll change this entry or any of this entry and keep everything same. So D2 and D1 will also will differ in only one entry. So I'll keep on doing this for k times until I get to dk, which is the data set D2, right? So do it for total number of k times total. Right? Do the same operation k times total. Here k is 3, so maybe one more is required, but you get the idea, right? So now D0 and D1 differs in only one entry, so you can do DP guarantee for that. So what is that means? So if I write,
Please write this section.
Oh yeah. what we'll have? So I will now write dp guarantee for d0 and d1. So probability of d superscript 0 and d superscript 1. Probability of a d superscript 0 is in S is less than or equal to e to the power epsilon probability of a d superscript 1 belongs to S, right? Because just defined in one entry. Take this, do it for d1 and d2. So this will be again e to the power epsilon. This will be less than e to the power epsilon probability of a d2 belongs to S, right? So what we'll have? We'll have e to the power 2 epsilon probability of a d2 belongs to S. Now do it for k times, total number of k times total. We will get e to the power k times epsilon probability of a dk belongs to S. Okay, so now we have defined d0 as d, right? So you see, right, d0 was d1 and dk was d2. So this is basically probability of a d1 belongs to S, and this is basically probability of a d2 belongs to S. So we have established that probability of AD1 belongs to S is less than or equal to e to the k epsilon into probability of AD2 belongs to S. So this is what the proof is. Okay, so all the proofs are done. I think that's for today, and tomorrow I will talk about one more mechanism. So today we have talked about mechanisms like Laplace, right, which takes an query's answer and perturbs by adding some noise to the answer, right? So these kind of mechanisms are called output perturbation. Takes an output answer and just perturbs it using noise. So what can we do for other mechanism which doesn't do that? So we'll talk about one mechanism tomorrow, and then I think that will be it.
Let's thank the speaker for today. So we have a 20-minute coffee break. So we will resume at 4:20. There will be a talk by Prahlad, KVM.